up here to the top, and you can go to design and quick layout. And that's my quick layout. It's my favorite one. You know, it's in the chart title, it's all this stuff. I think I'll show this again real quick. Got all these options, got so many cool things. It's so nice.
Gary! I was just looking for the sports channel, Gary.
Hey everyone, how are we doing? It is Thursday. We've got, let's see here. What is going on? Maybe I disconnect. Nah, didn't break it. I updated the stream decks, and so I have, for anyone who streams, should not mess around with things live. So I've updated these right here, all my buttons. I'm pressing the wrong buttons. Hey, what's up, Campbell? Good to see you here. What questions do you have? What are you working on? We can talk about whatever you're working on. I was updating stuff in the background. Should never do that. Should never go off camera there. Go off screen. Never update anything. You'll break it. BAS assignment 6, 320, I think, right? So go ahead. Feel free to, which one are you working on with 320 assignment 6? We can go ahead and talk about that here. I'm sure people will be very happy if we put some of that in office hours. And let me get assignment number 6 up. Let's do it. Let's talk about assignment 6. We'll have it up here in just a moment. There we go. Looking good. I think we're good. There we go. Let's see what questions you have. Got so much. I want to clear this out. Clear all this. And I think we're good. And let's do this. Don't save. Reopen. Good to go. Okay, we are good to go. Let's take a look to see what questions there are. What questions do you have, Campbell? Which questions do you have? I've got the assignment up and ready to go. Assignment is good to go here in the background. It is kind of small. We'll go over to the main screen. Let's do the main screen. Class is over. Question time. So with this right here, we're doing a bunch of regression. So we have all different regression models that we are building. So we can try to build some of them. Right here, we need the homework packet. We'll be using that some. Loading up library reg class, which everyone should have by now. You do not need to load an ex3 abline. It's loaded right here. There we go. Question A, scatter plot with options. So with this scatter plot right here, it's probably telling us to make a scatter plot of, I think, the shell weight and the length. Let me bring up, class is not over, Tom. I'm going to bring up the homework packet here. So hard to find out on this computer, the homework packet. I really hate the way searches work on a PC. It's very counterintuitive. Search on Mac works way better. I don't know why on PC it just can't search your files a lot better than the way it searches on a Mac. Macs win that one. You win this one, Max, but you have not won the war. I use Macs way more often. Well, I used to. Now I've got this PC and I use it way more often. For question 1B, it says to fit the model. How do I do that? So how do we fit a linear model? 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 We'll do this. ex3.ab. There we go. How do we fit a linear model? How do we fit the linear model? Can't zoom in anymore. So fit the linear regression. How do we fit the linear regression? Make a scatter plot using these right here. You can do it with the visualize also. So I will accept that. Please tell me the Gary's takeout points. But I'll show you how to do that real quick. Someone was asking about it earlier. So was it Campbell? Did you ask about this? I think did you ask via email? Someone was asking via email earlier. And so how do we fit? Let's do the scatter plot. I will do the scatter plot. What two variables are we analyzing? We're analyzing the meat weight and diameter. So we want to predict meat weight from diameter. So let's go back to here. Meat weight from diameter. And then data equals ex3 abline. And there it is. We need to add in the extra features right here. It says it wants to do PCH equals 20. That is the point style. And then CEX, what did it say? CEX equals 0.3. Something close to that. Yep, those are the ones. You mailed about 1A. Yeah, this is, you can do, they are similar because I guess technically, and please tell me if the graders take off points, because the whole point of this is to visualize it. We won't fit the line quite for this. You can use the visualized model for it. It'll basically come to the same conclusion. But how do we make a linear model? How do we make a linear model? Wow, there's the plot. How do we make a linear model? So how do we go about making a linear model here? It says fit the model. So what is the format for fitting the model? We're going to save into something. There's the hint. Yep, the LM. So it's LM y tilde x comma data equals. It's very, if you look up here, we did this up here. We did y tilde x comma data equals. So there's the data, and let's grab it. Y tilde x comma data equals. And let's go right here, and we fit the model. So now it says visualize the model. There's the visualization of the model. And you can still do PCH here. The CEX changes something different. So I'm glad you're here, Campbell, because I'm kind of against it now that I rethink it. It should change it. Oh, I did a period. I was like, what's going on? It still changes the point style right here, and that's the point style, so it's changing it. The CEX changes the size of the legend right there. So it'll change the size of the legend to make it really small, which you don't want it really small like that. You want it a decent size. I'm wondering, why'd I go back that small again? There we go. That's a decent size. And you can use really crazy points right here. I wouldn't do all this right here now that I'm thinking it over. I'll just use the visualize. It's going to make a nice graphic. And then you've got all the arguments right here. And I try to make my code look as nice as possible. I do like y tilde x comma data equals. But hopefully then we can see that this is the next argument and the CEX is the next argument. So what do you think about next, Campbell? What do you think about next? Which part do you think about next? I just don't want the grader. The truth is that both these graphics, if you look at this one right here versus this plot right here. So PCH is point style and CEX is character expansion. And so it depends what it's attached to. So the character expansion here will change the size of these points behind my head. So watch those points behind my head when I change them to be really crazy big. So now they're huge. Or watch when I make them really, really tiny. Itty bitty 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 bitty. And make them even smaller. So, is that as small as they go? Really? I think if we zoom in, they'll look even smaller. Maybe that's as small as they go. There might be a limit. Well, that is as small as the points go. But there really is no upper limit on the CEX, which stands for character expansion. There we go. That's a beautiful graphic right there. That deserves it. That's A+ work right there. Don't make a graphic that looks like this. So the character expansion is the size of the whatever we're expanding. Do we need how to use those? It tells you what to use. So it says use CEX3 and PCH 20. But the PC, you can't really see it there. The PCH changes the point style. I can't remember what the acronym stands for PCH, but it's whatever the style of the point is. So the style, you see those are stars. If you can tell, here we'll do 2. They'll be even bigger. These are now stars for the points. So you can do these things right here. You can even add in, but it says use 20. And then it says use 0.3. You could even do col equals purple. I mean, I don't mind if people do a little bit different. Please tell me if the graders take off points. But this is with PCH 20 and CEX 0.3 and the color being purple. So that'll do right there. You can do some really interesting stuff with this. Really fun stuff you can do. So keep asking questions. What are people wondering? This is how this code works right here, the plot. And just trying to understand the arguments better can hopefully help and create some understanding right there. If you notice, this plot right here is the same plot we're getting right here. We just have the line through it. How do we write the equation for the transform model in Q1C? Sure. So we need to first find the transformed model. To find the transformed model, we're going to go here and go to find transformations. And figure's too large. Of course it is. All here is always crazy. There we go. So if the figure's too large, you just increase the plot window. So what power will we raise x to? What power will we raise x to? So we need to define the y transpose and the x transpose now. What power will we raise x to? Oh my gosh. 2 seconds. my brother and my mom called, and I was like, and they called like 4 minutes apart. I was like, I hope nothing's happening. So, yep, gotta check in. I was hitting the mute button, so it was my mom. My brother called. It's like, hope nothing going on. Don't usually get back-to-back call from family members. They never call. What button is it? Never call. They call. So let's go here to the y transpose. We are predicting the meat weight. The meat weight we are predicting is this right here. And so we're going to create our transformed variable, not transposed, but transformed. And then we're going to create the x variable right here. And I know it's not the right variable yet. There's the power to which the x is raised. Oh, yeah, that was awesome. Yeah, that was so much cool. That was so much fun. Yeah, it was for that. That was one of my favorite lectures I've given. That was so much. I'm so glad you were there for that, Campbell. I really liked that lecture. I spent a lot of time working on that with the effects and stuff. That was, that was my favorite lecture I've given so far ever, probably. So it was for the last lecture. That's what it was for. It was a lot of fun. Jackie Jacobs was there. She did a great job. It was a lot of fun. We talked about Spider-Man Into the Spider-Verse. I kind of gave the story of my life, and I was like, I just want to hopefully let people see that I've gone through a lot of craziness and things I didn't expect. And, you know, even going to Texas, you know, like, I think this was almost exactly a year ago, so I didn't know I'd be in Texas right now even. Yeah, because we weren't in COVID times. You remember back when your family could come and visit and we could all go to a big room and hang out together and, you know, not be freaking out? I freak out all the time. So, yeah, no, it was awesome. Well, it was just, the whole thing was awesome. And I really appreciate getting the opportunity to do a last lecture. It was really, really kind of special. So I loved it. You see, am I putting in 300? Yeah, I know. And Jamie Foxx might be back. Yeah, like, dude, whatever they're doing with Spider-Man is going to be huge. Oh, thank you, Campbell. Thank you for saying we had big shoes to fill from last year. I really appreciate that. It was a lot of fun. Got to talk about Back to the Future and stuff. I was like, what movie references do I put in here? I wish I had the skill sets I have now because I've learned more video editing. I'd put in even more crazier things like things on fire and stuff. I don't know. It was so much fun. I shouldn't critique my own work, but I just like improving what I do every year. I'm always trying to learn new things and improve and make more fun. And I don't know. It's just a growing process. We all grow. And so I'll talk one of these days. I'll be like, maybe I'll do another last lecture sometime, like another 5-10 years from now. But it's so hard to say, what would you tell people if it was your last lecture? Like, if this is your last lecture, what would you talk about? And like, it's kind of, I hope it's not lame to say I'd talk about myself, but it's like, here's what I've accumulated in my life. Here's what I've learned over time. And I want you to learn from what I've learned and see maybe that, you know, you have to take these leaps of faith. Like, even like going to Texas was a leap of faith. So, you know, I drove down here in one day. I drove to Texas in one day. I did that twice in my life, which I think I talked about when I did archaeology. So little did I know when I was giving that lecture, I'd also be doing another one-day drive to Texas. Driving 14 hours in a car is not my idea of fun. Living with my fiance is awesome, but driving the 14 hours to get here I don't like driving 14 hours. Not fun. So we need to write this transformed model, right? Let's write the transform model. So when you have a transform model, we need to raise the x's to those powers. Now here's a really cool trick. Really, really cool. We mentioned this in one of the classes. Sometimes I don't say something in one class and then I feel bad and I'm like, I talk about a cool trick and then I just don't say it in another class. So we have here the coefficients. What is the coefficient of the slope? We should be able to identify those like this. What is the coefficient of the slope? What is the coefficient of the slope? Silence. That's the coefficient of the slope. It is. Great job, Campbell. That is the coefficient of the slope. And we have right here that we need to write the model. Let's write y equals b0 plus b1x. Now, isn't this just basically all the models? Isn't every model basically this model? Isn't that kind of true? I mean, yeah, kind of. But what is the name of our x variable? This is y equals b0 plus b1x. And the name of our x variable is going to be, well, that's our y. Of course, I grabbed the wrong one. And then this is our x. Okay. So we're a little bit closer now. We're a little bit closer. So now we've got the names of the variables in there. Now we just need the coefficients. So now we grab our variable here for the coefficient. I think it doesn't add those spaces. Yeah, it doesn't. That's interesting. I remember that. And now we add this. It's going to, I don't like what it's doing there. I just want to make it, there we go. Sure, why not? And there we go there. But we're not done. What am I missing right now? What am I missing to almost make this perfect? I'm so close to having the right answer. What am I missing from my transformed model? What am I missing from the transformed model? My hair is getting so crazy. It's just like, it flies in my face through the fan to keep it cool in here. The powers, exactly, the powers. And if they released like an alternate Spider-Verse movie where they just took outtakes or alternate ideas, I would watch that in an instance. If they were like, oh, this was... Because they've released some alternate stuff with alternate scenes with Peter and Miles, and I would just watch that. I know. It'd be so good. Just like, I don't care if it's just as good. Just let us see more Spider-Verse. I guess they're working, Disney's working really, Disney, yeah, Disney's Spider-Man. Spider-Man's Disney, I think, right? Or no, Spider-Man's Sony, right? And then Sony leases it to Disney because there's been a whole problem with that. But that's the answer right there. I might just try to do different problems, but yeah. So, yeah, Spider-Man's Sony, and Tobey Maguire did great. Andrew Garfield, decent work, Andrew Garfield. Decent. Like, you're welcome, Campbell. Decent work, Andrew Garfield. We don't talk about those days. Choose the transformation with the highest R square. We did all that. And then Miles Morales is amazing. So check whether the transform model reasonably reflects reality by running the check regression. Statistically, what assumptions, if any, are passed? So it's asking statistically, and we need to go into good detail on this. People should be lucky I don't grade all the assignments, because I would be a little bit harsh on some of these right here. So when you look at this right here, what is the first thing we do when we check assumptions? What is the very first thing we do when we check assumptions? When we check assumptions, we should always do what first? Checking assumptions, you look at the what's first. P-values, nice job, Brian, right there, 100. And we'll look at normal here in a moment. We'll look at that in a moment. We'll look at the p-values, and then what do you see for the p-values? What do you see for the p-values? The p-values here are what? Is that good or bad? The p-values here are very this. The p-values here are very, very this. Is that good or bad? They are bad. They are less than 0.05, which is very, very bad. And why is it bad? Because we fail the conditions. So we say, well, isn't 0.05 good? Less than 0.05? Below 0.05 just means reject the null. And reject the null means evidence for the alternative. The null for this is that linearity is good. So you're rejecting that linearity is good. You have evidence linearity is bad. The null for this is that equal spread is good. So you're rejecting that equal spread is good, and you're saying you have evidence that equal spread is bad. The null for the third one is that normality is good, and you're rejecting that normality is good, and you're saying you have evidence that normality is bad. So where do we really see the problems here? There's one area there's one area where we really see problems. And is it linearity or normality? That's my favorite question. It's like Brian's top question that will be on the test. I say that, and then sometimes I forget to put a question like that on there. It's normality. Yeah, it's definitely normality. The linearity looks to be fine. If you want to look at the linearity, you can look at it here, but you could also look at the linearity by going to visualize model, and we're doing the transform model, right? So here's the linearity of it. I really don't see that the line would bend around it. I mean, I guess that's probably why it's failing. Do you see how it goes up and then down? And we could see this if we use the choose order, which looks at polynomial fits. You don't need to know this stuff. We will be talking about it later. And there's the bends I was talking about. You remember how I said it might go up here and then down a little bit here? It's just the residuals. Yep. It's a scatter plot looking at a prediction based on normality and what we observe. So it's seeing how closely it follows what is predicted. And imagine it was a one-to-one prediction. Like if what we expected via normal was actually what we observed, then everything would be perfectly in line and it would follow literally a line. So when you think about what it should look like if it's normal, it should follow that one-to-one prediction. So when you look at this line right here, this line is showing you what you would expect given it's normal. You see how it kind of goes. I wish I could augment this plot. I need to vanish. But if you look down here where 0 is at, 0 hits right here where 0 is at. And then this is down at where -3 is at. That should be because values if normal and then observed values. And then this line right here, I feel like the line is not perfectly showing it. But what we're trying to see right here is, do the residuals follow what we would expect given it's normal? And how far away is it? And the residuals do not show it. So it's a scatter plot, but don't think of it as a scatter plot looking for a linear relationship. Think of it as a scatter plot trying to tell you if the observed values follow the normal. And the answer is the observed values do not follow the normal, because you can see here the points going away. A lot of extreme low residuals, a lot of extreme high residuals, and that's where we see this right here. All these points are kind of, this point here is that point there. This point here is that point there. This point all the way down there is that point down there. Because it's literal residual distance and how far it is away from the line. So yeah, these are, it's got major problems, but overall, I'd say it's fine. It's okay. Just, if you're going to write these things up, you want to mention that. You want to talk through, how bad the problems are. And I wish I could just say, write a report on regression. I wish that could just be the final. I could just say, write a report, like take 1 week and write a report showing what you know in regression. And that'd be your whole grade for the class. Everyone would probably freak out. But I could analyze better what people understand and how important they know it is to kind of be exact with your words. And when you look at these conditions right here, especially, you want to think, okay, this is an issue. That's immediately what this says to me. We've got issues over here. I need to look at these plots as long as there's a sample of 25. There is. So now I'm going to look right here and I'm going to say, okay, linearity doesn't look to be as big of an issue. I do see some outliers here and I see some outliers here. Maybe it's a little heteroscedastic because it is getting a lot wider. So that's where I see the equal spread failing. And then the normality of residuals back here, I see big problems. Is the residual plot not predicting like the QQ plot? No, this just has predicted values too, because it's going through as the predicted value gets higher. So it's kind of showing you, but it doesn't say if normal. So it's not if normal. Does that make sense, Campbell? It's not the predicted values if normal, where the other one has residual values if normal. So this one has if they're normal down here. That's kind of key. And this one just has the predicted values as we go through to higher predicted values. So it's basically like moving along the x-axis, but it's moving along the y-axis. And that's telling you how much you miss each predicted value by. Because especially in the multivariate sense, if you were to look at the multivariate sense, it'd be hard to look at one x-axis. But this is basically the same as increasing the x-axis right here, but it's just doing it in terms of y. Since there's only one y, we can talk about, here's this predicted value of y, and this is how much we miss it by. Here's this predicted value of y, and this is how much we miss it by. But that predicted value of y, if we're doing a linear model with just one variable, would only occur with one specific value of x due to the linear combination of x and y. So right now, it's just like saying if you have higher values of x, you'll have higher values of y. So we should see down here that the lower predictions are going to have really high misses. And can we zoom in on this? Oh, this is our untransformed model. Sure, let's look at that. Let's look at the untransformed model. Its residuals. So if you see here, the lower values of prediction have more of the misses, and you see this tail right here. That tail is this tail right here. So that same tail shows up in this plot. Here's a really high residual on the end. Here's a really low residual, really high residual. And then we take a look at here, and there's the really low one, and the high one's going off the edge. Sometimes that happens with this graphic. It goes off the edge a little bit, and I don't like that. I don't know why. I think Petrie did it so it encompasses like 95 or 98% of the data due to extreme outliers, but I might try to update his code. We've talked a while about updating it all to ggplot, but I just haven't had the time. And as my skills get better, it takes less and less time, but then I learn more and more things. And so the problem is I'm like, oh, but you could do this and this and this and this and this. And the more you learn, the more time it'll consume because you'll know more techniques and more cool things you can do. What additional questions are there? Which ones are people working on? We can knock out a few more here. Why not? If you have a question about any of them, just let me know. Be like, Brian, this one right here? Let's talk about it. You can work on any question. Let's see. So I think you have to untransform it next, don't you? At some point, you have to untransform the model. Since we failed the test, what does that mean? That means there's an issue. That means there's an issue with all three of these. But remember, when you fail a test to look at the plots, if I were to report to somebody, what would I say my primary concerns are here? Well, one, we fail all three tests. That means that linear regression is probably not appropriate. But my biggest issue is going to be with which one. Because when you fail these, you have to, if you have a large enough sample size, look over here. You have step 1, step 2, step 3. And when I get to over here, I have to say, well, how badly do I fail these tests? And really, I'm saying the big problem is the normality of the residuals. So I think here's the biggest problem. So maybe linear regression might have its problems, but we still have an R-squared of 95.65%. All models are wrong. So this regression model has problems. It has big problems with the normality of residuals, and that'd be my big note on it. That there are some extreme misses we have towards the upper end, which could also point to some heteroscedasticity. So if I was writing a report about this, I would say, this model is excellent, explaining 95.65% of the variation after the transformation, but I'm just knocking things over. This model is excellent, explaining 95.65% of the variation after the transformation, but there seems to be major problems with the conditions for the regression because we see extreme heteroscedasticity, creating large residuals at the upper end of the predicted values. This is also noted in the normality of the residuals plot, where we see extreme deviations from the low residuals and extreme deviations from what we would expect on the high end of residuals. So I would have hesitation towards saying this is a great model. It does seem useful with 95.65% of the variation explained. That's almost 96%. That's tons of the variation in the meat weight explained by this model. But I do have some hesitation due to extreme outliers present. So overall, it's a great model, but overall, I give it a B+. It's really hurt by this. This is where it just like left a page blank on the test. It was doing so great. It had such a good R-squared. And then it left a page blank on the test. You're like, you were acing the test. You were going to ace everything. You were doing so good. We could even maybe forgive this heteroscedasticity, but these outliers kind of induced by the heteroscedasticity. So when you look at how bad the conditions are, it has to be a holistic view. You don't want to say, good, bad. You want to say, you don't want to just say they're good, they're bad. You want to say, what you think about them in a larger viewpoint, because this is really bad and this is kind of bad. Does that make sense there, Campbell? Especially for the test, but I'm probably not going to do a written one on this one. I'm going to save once again, I can't make this any more obvious. What do you think will be a written question on the test? Interpret the what of a what? I don't want people to be shocked when they see this on the test. Like, hey, what's up, Jessis? Good to see you here. Feel free to ask questions. We're working on some 320. Feel free to be like, hey, can you talk about this one? Can you show us how to do this one? Or anything you want. But I don't want people to be shocked on the test when they see interpret this. I might even send out a reminder for Emery's class to be like, hey, just so you know, you really need to know how to do this. So everyone's on track and no one's shocked when they see it. I don't want any class to have an advantage. Anyway, we could do the log transformation on Q2. Yeah, sure, why not? Let's do that one. We got enough time. Now we're working on the homework's good. Let's do it. So we're loading up the EX3 housing data set, and then it's a log transformation. So are we predicting, what are we predicting? Price from area or something? So we are predicting price and area, price from area. We are correct. So I'm confused because one of your reviews talks about a file that we work on the midterm, but on Canvas it shows as an lockdown test. Are you talking about the take home? Are you talking about the take home, Jessica? It's a recent video, right? It's one of the class videos, right? I'll show. Let's do that real quick here, and then we'll hop back to this question. So let's see. And let's take a look. Okay, so good questions. There are 2 quizzes. There's 2 quizzes, and then there's the take-home test. And because 320, right? I'm 99.9999999% certain. There's 2 quizzes, and the 2 quizzes are under the assignments. You should also see them in your upcoming. So you have 2 quizzes, and so your quizzes will be, there's the bonus for the quiz. You'll have review for test 1, and this is the 10-question quiz, which is going to be very much like the actual test. So there's the review quiz for test 1. It counts for a grade. I was going to call it practice, but then I was afraid people might think it's not counting for a grade. But this is due by Sunday, and this counts for a grade, but it has bonus, and people have been reporting it takes them 10 minutes. So make sure to do this one. This is the review quiz for test 1, and then there's also the test respondus right here. So this is 2 extra points on your test. It's to ensure you know how to use respondus, which I'm sure many people know how to use respondus, but the goal is that when we give the test, there's not many problems. So what better way to ensure that there's no problems than to put up a free bonus of 2 points if you just complete it, and they're very simple questions. Campbell, have you done this one yet? If you haven't, it's you might have already. I'm trying to remember. I graded some this morning because you have to put in your name, so I had to manually grade those. But this right here kind of shows you what the respondus will look like, and it's 2 free points on the test. So that's a huge opportunity. Yeah, exactly. And how long did it take you? Maybe 1 minute, 2 minutes? Like, hopefully it just took you seconds. Like you log in, you did it, you were good. 1 minute, easy. So is the first one multiple attempts? Yes. The first one we just mentioned is infinite attempts and shows you the answers. So when you get them wrong, it even tells you what you got wrong, and it doesn't switch the problems or switch the answers. So I was telling my fiance about it. She's like, oh, you give him a lot of work. And I told her about it. And she's like, oh, that's easy. She's like, it's fine. I was like, okay, good. Because I kind of run my plans by her a lot of time to make sure. I'm like, what do you think of this? She's like, she'll tell me if it's a good or bad idea. She'll be like, don't do that. So she is to thanks for a lot of my hopefully good ideas. So she's definitely turned down some ideas. I'm like, man, I can't believe I thought about doing that idea. So I was like, I should give everyone A's. And she was like, yes. And I was like, I should have done it. Should give everyone A's. I'll put the blame on me for not giving everyone A's. But with this right here, this one takes, people are reporting about 30 minutes on this one, I think, or 10 minutes? I think people said 10 minutes. And then people are like, is the test going to be this easy? But here's the thing with this one. If you do this one and then it's really tough and you don't know the questions and you make a 40 on it on your first try, remember that you only get 1 try on the test. So this one might be easy because you get multiple attempts, but on the test, you're not going to get multiple attempts. So if you try this one and you're like, oh, I did so well, and then you make a 40 and you're like, what? Then be careful because there's maybe a disconnect with the information. So use this as a gauge to see where you're at. The better you do on it without notes, then the better you're at. But you do get a cheat sheet for the test. So the better you do on this review quiz for test 1, the better you are on the test. The last thing, but not least, is going to be the take home. Where are you at, take home? So the take home is right here. You will download the following file and you will open it inside of R. If you have any issues, let me know. Here, I'll get the file downloaded and open inside R. Class and over, just pulling up the screen right here. So you will take the file. I'm downloading right now. You will open the file inside of R. I'm going to open the file. And there we go. The file is open inside of R. So here's what it will look like. You will have the file open inside of R, make.exam. And when you run this right here, you will just go down here. I would go to a new sheet. It doesn't matter where you run it. You can run make.exam. You put in your ID. My ID is 20. Put in your ID. It doesn't matter if you put in the zeros or not. It'll make your exam. If there's any issues, please let us know immediately. No worries, no worries. Please let us know immediately if there's any issues. So as soon as if there's any issues, let us know. Say, hey, Brian, my thing won't load. This won't load. A lot of people I've noticed have gone down here and have clicked on the make exam, and they're like, okay, what do I do? How do I complete this? Is not making the exam. When you make the exam, it'll actually make the file here. So 2 seconds again. So the file it will make will be stored on your computer. I have so many of these. It did make it, right? Okay, it did make it. I was like, it better have made that file. So there it is, the exam F for 2020. So it's, there we go. What is the best way to study for the respondents exam? I'd say definitely going through the notes and looking at any portion of where we have things like in the box. Also, if you post practice questions, I might use those. If you put under the practice test question on the Discord, I look at that. And during the summer, I definitely for 474 took a lot of their questions from suggested questions. I think that's a really great way to source students to build questions, to get them to think about it. And then if you build a question and it gets on the test, you probably know the answer to it. And then if other people didn't look at it, like, oh, the question was out there and the answer was out there. I wish I could just give people 500 questions and say, learn. I mean, I wouldn't want you to just sit down and try to memorize 500 questions. I want you to understand the concepts. So the better thing is literally what I'm saying is where you come up with your own questions and your own answers. And if you can come up with questions, then you're good. Like, imagine I asked you a question that said, interpret the slope of this model. So if we go here and we say, and then we'll do the other one. I have not forgotten. EX3 housing. Okay, let's do it. We're not going to do, well, yeah, let's do it. We're not going to do the transform model yet. Okay. So area is in square feet. Price is in thousands of dollars. This is the untransformed model. And interpret the coefficient of area. Interpret the coefficient of area. This is really big for the test. Since it's in lockdown, exactly. You won't. It'll be very similar to. It'll be very similar to the one you're using. The lockdown one I post, or it'll be very similar to the practice one. The test will be very similar to the practice. So there'll be a written question. I'll probably even release info saying there will be a written interpret the slope question. Do not be shocked by this, and I will grade it very harshly. I will let people try to interpret this slope coefficient right here, and I will grade it 0 to 5 points right now. Who can interpret this area coefficient? I will grade it 0 to 5 points. I'm scared. I'm going to really hurt someone's feeling if I give them 0 points, but I'll tell you honestly what I'll grade it. If you interpret the coefficient of area, if you want, give it a second or two more for people to think it over. If you're watching this right now in the future, try to interpret it. Maybe say it out loud. I don't want to even start it because then people will know what we're looking for. I mean, I'll tell you the answer in a moment. But how would you interpret the coefficient of area? How would you interpret the coefficient of area? I could just take this question and put it around the test. Interpret the coefficient of area. Interpret the coefficient of area. We'll give it 1 minute. Okay. Try typing it out. Let's put 1,000 points on the table, first person to get it. I'll grade it 0 to 5 points. Let's take a break, relax for a moment, and then we'll do the log model. Interpret the coefficient of area. I might jump in and give the answer in a moment. The coefficient of area is going to be, I feel like someone's typing the answer, 2 houses that differ in their area by 1 square foot are expected to differ in their price by $158.95, where the house that has a larger area is expected to have or the house with a greater amount of area. Just trying to give the right grammar. Grammar's the hardest part. Where the house with the more area is expected to sell for more. 2 houses that differ in their area by 1 square foot are expected to differ. Oh, Campbell right there, 1,000. And then we don't have to do the otherwise identical because it's only simple. No worries though. I probably would not take up points for that. Like I really mean that. It's like, oh yeah, it's like putting a cherry on top of the sundae, and you're like, well, when you're I mean, I'll take it. So, but differ in their size of area by 1, by their square footage. So I'd be probably okay with that. We'd probably need to say in the problem that the area is square footage of a house are expected to differ by the price by this, where the larger area is expected to have a price higher. Yeah, I'd probably give it a 5 because I grade a lot of these, and that's going to be near perfect. Like near perfect is a 5. It doesn't have to be perfect, but near perfect's gonna be a 5 because that has everything we're looking for right there. Yeah, don't worry. That's where I'm like okay, there's the smallest of issues, but I'll read things that just say we'll say interpret area, and I'm very sorry if this is you on the test. You know what someone will put as the answer? The question will be, this will be the question. Interpret the coefficient of area in context of the problem. And the answer the person will give, it's all right. This happens every semester. Someone will just put this. That's the answer they'll put. That's their full answer. Then I'll go and I'll do things like I'll go in and be like, interpret, and I'll like bold it and underline it. And then every semester I'll get someone who just puts 158.950, or they'll put the intercept. I'll be like, oh my gosh. How come it doesn't need the other? Because it's not a multiple. Since it's not a multiple, in the multiple world, we have to acknowledge that they're otherwise identical, but there's only one characteristic right here. There's only area. So we're only comparing houses that differ in the amount of area they have. We're not saying that they differ in the amount of bedrooms they have, or the neighborhood they're in, or the year they were built. So then if it's a multiple model with year where they were built, neighborhood they're in, we'd say two houses that are otherwise identical that differ in their area by 1 square foot are expected to differ in their price by, yeah. And that's why it doesn't need it, but it doesn't really hurt it. The log-log model, breakpoints cannot be saved. Oh no. The log-log model, let me write this right so I don't forget. Log-log model. So log-log model, to get the log-log model, we need to go here, and we need to go to y transformed, and we go log 10 of ex3 housing price. Copy. And now we go to x transformed, log 10 of ES3 housing area. And I think that'll do it. There we go. We build our linear model. Sure, why not? No, let's not overwrite it. There we go. Let's go to transform. There we go. And now we can look at it. There we go. There is the transformed model. We can also visualize it. And there it is. What did the original model look like? Let's compare it to the original model. Really? I'm going to hit all the wrong buttons. It was a little more heteroscedastic. The original model has a little more there's some nonlinearity too. There's nonlinearity and heteroscedasticity. And what was the summary of this model? 67% of the variation versus this model here has 72.6. So the increase in R squared is about more than 5%. So the p-value stays the same even though it's transformed. The p-value actually went, it might be hard to see, but the p-value went down. The p-value went down because the F statistic went up. So the F statistic here is basically like a T, and the T squared is the F. So you see the 32 right there. It's now 37, and 37 point this squared is that right there, the 1384. But you don't need to know things like the T squared is the F. But we mentioned this in class. I think, are you in afternoon class or morning class, Campbell? We were talking about this in morning class, that the T statistic tells you how significant something is. And afternoon, no wonder. Yeah, we were talking about this in morning class a little bit. Do you see how this model here has a, you can see both. There we go. The T statistic here is lower, and the T statistic here is higher. And the higher the T statistic, the what the model will be, or the what the p-value will be. The higher the T statistic, the what the model will be. The more extreme the T statistic for the slope, the p-value will be lower, and then that's more significant. So it's just not carrying out enough decimals. So the p-value has gotten smaller. It's just like 0.000. There's so many zeros now that it's no big deal. So there really is. It went from super significant to super duper significant. So it's significant in all ways. Does that make sense, Campbell? So the model's more significant. So the higher the T, the lower the p-value. Bingo. Yep. Great note, Jessica. And that is for the x variable, not the intercept. The intercept has nothing to do with significance because the intercept could go up or down. And what slope do I have for this line right now? What slope do I have for this fake line right here that I have? And I could actually build this. I'll show this. So if you see the line, yep, 0. And this would be an insignificant line no matter what the slope is. We could build this with y store into 8 plus, and then let's do 0 times x plus random normal. And then this should do it, right? Just random normal, one number. Okay. X not found, of course. X is the vector 1 through 10. That worked. Let's do 1 through 100. Okay, cool. Let's go here and do a model of y tilde x. And let's do a summary of it. So if you notice, oh, we almost got something significant. Are you kidding me? X. What should be the randomness? Is it not regenerating it? What? Oh, let's do this. I know what it is. There we go. There we go. There we go. Is the respondus all multiple choice? There will be fill in the blank. There will be multiple choice. There will be numeric entry. So there'll be multiple choice, numeric entry, and fill in the blank. And so this is a fake model I've created right here. And tell me about this model. What is the actual slope to this model? What is the actual slope to this model in this fake example? Oh, no, 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 no. We wouldn't do that to everyone. What is the slope to this model in reality? Don't look at the randomness. What is the actual slope to this model? The actual slope coefficient of this model is what? I'm trying to get a very bad one here. The actual slope coefficient is 0. So it's just randomness that you're getting all these different values right here. I'm trying to get a really high p-value. I should have stopped. There we go. And you see how this is basically 0 right here? But you see how the intercept is significant? I can make the intercept insignificant by going down here and making the intercept 0. And now the intercept is going to have a very high p-value of 1. Oh, because of the randomness. The intercept could have different p-values due to randomness. But the p-value for the intercept is also going to be jumping around like this. If you notice, the intercept is now at 0, and the slope is now basically 0. And both of these are insignificant. Because this model is just complete random points from 1 to 100 with complete random z-scores. So that's what this looks like, is complete and utter randomness. But by random chance, you could get a model that is statistically significant. Like, I'll try to find one with a statistically significant slope. This model right here has a statistically significant slope, and it's completely by random chance. Notice how when the t-value goes up, the p-value goes down. There's also something interesting about this. The t statistic here is basically 1. And so I was trying to reinforce this morning. With a t statistic of 1, we can guesstimate the p-value. A t statistic of 1, if you take a look at this, we'd go here. And with a t statistic of 1, what would be the area outside of a t statistic of 1 and -1? What is this area very close to when we use the empirical rule to estimate the p-value, which is the probability of a result as extreme or more extreme? Here's a hint. So what would the p-value be very close to? 32%. Yep. Nice job, Campbell. Yep. So that's just an estimate right there because it's not exactly 1, but take a look. It's 31% basically. And you can see this when we generate p-values that they're related to the t. So the bigger the t, the more you move out that interval. It would just move it out further. Like this one is small. We'll find a larger one. Those are all small t's. Now we get out. There goes another one. All these small t's. There's a bigger t. Not too big yet. Where's the big t? We're just not looking out on the randomness. Wow. Oh. Well, look. The t's are basically the same. That's interesting. I don't know. I have so much fun with this. Just looking at t-scores and stuff like that, it's kind of cool. But you see how these t's are basically the same and the p-values are basically the same. And you also notice it doesn't matter if the t is negative or positive, because when you do this, you reflect it on either side. You reflect the t on either side. So it doesn't matter if it's -1 or +1. And so this really hits upon the concept here that this t statistic will get the same p-value whether it's negative or positive, because it's going to be the reflection of either side. There's another concept we should know. How is this t-statistic found? Can anyone show the mathematics to get this t-statistic right here? What would you do to get this t-statistic right here? Because I'll leave things blank sometimes in output, and I'll be like, find this value in this output. And so you don't need a big calculator for this. You don't need any sort of very impressive super calculator. The t-statistic can be found pretty instantaneously right here with any sort of calculator. How would you find this t-statistic right here? How would you find this t-statistic? Because we should know all the output. Whenever we get output, we should know it. We can take this value right here and divide it by this. And that is the t-statistic. The t-statistic is a standardized version of your estimate. So the t-statistic is basically your estimate in a standardized way. So every time we talk about a t, it's the same sort of idea. T's won't differ from each other. You can say, like, this is the t-statistic, and someone should know what you're talking about. What other questions are there? Campbell, did you get the log model and all of that? Estimate divided by error. Exactly, Jessica. You're totally right. Estimate divided by standard error. You're exactly right. Equals the t. Bingo. And then the larger the t, the smaller the p-value. Did you get the untransformed model? Did you get the untransformed model? My left hand just started, like, randomly hurting. I hate getting old. Like, let me just feel random pain. Random. So we have I thought we had the equation in here for it. It's in the book. Where's the book? Go to the book. Book has the equation. Here's the equation right here. It gives the model. And so let's go ahead and grab this. And let's show this. So let's untransform the model. It's probably not the spot where we're doing it. Oh, write the untransformed model. So it's right here. Okay. And we want to do it so we can get the price. Okay. How's this look? It doesn't look so bad. I might end up putting this right here and put a multiply and let's put the area right there. Okay, so this I think looks a good bit better now. Okay. So, yeah, let's see this one right here. We've got 8 minutes. Let's do it. So when you look at this right here, if you do the double dollar signs, double dollars, like Vash the Stampede, you can make the LaTeX work, the LaTeX coding, and you can write equations as the following way. So what we first want to do is remove the log 10 in front of price. And frankly, yeah, I guess, yeah, we can make it look like this. That's fine. It's a harder one to do then. What we want to do now, we have to remember some rules of logs, is how do we undo a log? How can I remove this log 10 right here? What cancels when it's connected to a log 10? Like what down here would cancel with the log 10? We could put something down here and we'd do something to this. But what would cancel right here? So imagine we have, like, let's take, for example, log 10 of 10. That's log 10 of 10. And then, so how could I then undo the log 10 of it? How could I undo the log 10 of it? Log 10 of 10, how is it undone? So if you raise to the 10th power, or whatever the log power is, these two cancel out. So these are the things that mathematically cancel. Does that make sense here, Campbell, as we show it right here? Putting it to the exponent. But yeah, exactly right. That's all right. Great job, Campbell. 100 points right there. So the 10th to the whatever it is, so we'd raise it to the 10th. Bingo. So then we go here, and we copy this, and we go 10 raised to this. There we goes that. And we go 10 raised to this. Because whatever we do on one side, we have to do on the other. It's basically distributing out a raised to on both sides. So now we've raised both sides. And what's really great about this is now when we have two things added up here, make sure I remember how to do this, because it kind of gives a hint of how it should look. Area raised to some number. So should we do assignment 6 before we do the take home? It'll help. There's a little bit. I think the questions on assignment 6 are harder. The take home doesn't have too hard of questions, but I would say I'd get as much done on the take home as you can, and then I'd start looking at assignment 6. I'd be like, I don't know how to do this one. I should review, and it'll help. It'll definitely help. I would say it's going to be a huge help to do that. And then we can actually multiply these together. That's correct, isn't it? Yeah. So when you have two things added together up here, you can actually distribute this out to be multiplied. So that's the way one of the rules works with logs, is that I got to make sure I put this in the right spot. Is it not loading it? Let me delete it and remake it. Because that should close. Oh, no. It's mad about that. It's mad about that. Cool. And then this right here. Wait. Try to make sure I do it right. Oh, and that'll go on the end of it. So then this is still log 10 of this. It's 10 to the raise of this. Yeah. So it's 10 times 10 to the... I so rarely work with logs. They're so much fun. So it's that. And so when you have two things multiplied together, you can distribute out, or you have two things added in an exponent, they can be... What does log do? Log basically pulls things in. So a log transformation takes extreme values. Because think about this. What is the log 10 of 1? It'll be 0. What is the log 10 of 2? It'll be... we're doing log exe. Log e, I mean. So there we goes that. And as we do this, it's only going to go up by 1 each time. So if you notice, extreme numbers here are just 1 apart. And so when you use logs, they can take extreme numbers and pull them in. So it transforms the variable and creates more of a normal shape to it, so we can better explain the variation between the two variables. So even though these numbers are like 1 million and 10 million, they're only one number away, but they're the same distance away that 10 is from 100. So 10 from 100 is a distance of 1 to 2, and then 1 million to 10 million is a distance from 6 to 7. So it helps us put things on a log scale to pull in extreme values and not have outliers having as much of an impact. So they're really good with outliers or extreme data. And so now, I'm pretty sure, so right here, I'm just like trying to make sure my brain just slowly, this can go to a constant. That's just can be solved. So 10 raised to the 1.21 is that's just a constant. So this is just a constant, boom. And then let me look at this. Area raised to some number. And then, is it not that when you have, I'm trying to remember. Oh, because these can cancel. This comes down in front of it, right? No. Or does that go on the back of it? Yeah, I think it does. I'm pretty sure. Someone correct me if I'm wrong. I feel so bad if I put this in a video. It's this right here can actually go and go back to here. And then once we've done this, these two cancel. Do I have something improperly computing right here? Where's the error? Up there wait. What's it not like? Area raised. Oh, it probably does not like this area thing right here. What does it not like? Oh, there's a double parentheses. My gosh, I am so blind. So I believe that is it. Like double check later. But I believe that should be the answer. Get the answer. Let me see here. Let me go look. Who wants to do algebra? Not even me. No one likes algebra. Sorry, algebra. That is our one of our ending notes today. Who wants to do algebra? Not me. It sounds like a song. Who wants to do algebra? Not me. Not me. I don't want to do algebra. I want to do statistics. That's what I want to do. I want to do statistics. I don't want to do solving equations. Who wants to solve equations? Where are you, answer? Yeah, it's the answer. So what I wrote. 1621. Yeah, look at that. Here, I'll show you. Just so we can confirm. Not I. I suck at algebra, now I thrive at stats. That's awesome. That's the way it goes. Yeah, I got the right answer right here. It is. It's good to double check. Make sure you have the right answers. There's the answer right here. Here's another way of showing the path to it. But it's just so, the big trick that I forget is taking this right here and putting this back here. Stats is where it is at. So that's the thing I can't. I'm like, wait, you can do that? You can take something right in front of that and put it in the power. That's what can do it. And once you do that, the 10 and the log 10 connect, so they cancel. So this cancels right here. But it's one of the harder ones. It's algebra. I rarely use algebra. I mean, it's important. I'd rather just put it into a solver and say, solve it for me. So that's why I kind of did this one too. Because if I'm like, I don't want to do it, I'll be like, okay, let's do it. Let's knock it out. So with that, hey, what's up, Jake? Do you know what coding I'll be graded? We sent out an email asking them to get it done this weekend. Sorry, Jake, I missed it right there. I was talking about how much I hate algebra. I love statistics. I hate algebra. Sorry, that's why I don't teach algebra. Why do we have to use algebra? But it should be graded this weekend. We sent out a reminder to them, and I said it needs to get done this weekend. So I was like, well, what about... I like linear algebra. That's so funny. I like linear algebra. I don't like algebra. Someone might be like, this is linear algebra. I'm like, it is? What? I like linear algebra. Calculus is all right. Calculus is here. Linear algebra is here. Regular old algebra is here. Trigonometry is off the thing. I don't like algebra either. See, like Mubot needs to be like, I don't like algebra. But yeah, trigonometry and geometry. Oh gosh, those are my worst. When I got to trigonometry and geometry and mathematics, I was like, how is this even math? What is this? Why am I dealing with shapes? Just give me numbers. Of course, the numbers deal with shapes, arc sine and tangent and all those things, and cosine, and people come up with some. I need to get better at that stuff. I tried again. I tried to turn on my math brain a few years back, and it hurt. It was tough. I got better at it again, but then it's very hard to get back into like doing high level mathematics. And I wasn't even that high. I was in like junior level mathematics probably. Junior/sophomore level mathematics, but it's tough. It's tough stuff. So good job to those who know algebra really well, high level algebra, especially. We're just dealing with canceling stuff out. So all that good stuff. Well, with that, I'll be teaching the next class here soon. Feel free to ask me any questions if you have them, but I'm going to head off here real quick and send me those questions, Discord me those questions. I'll be talking to everyone soon here. See you. Goodbye, Campbell. Great work. Keep it up. Great seeing you, Jessica. Good seeing you, Jake. And I'm trying to think if anyone else was here. I think we had Ryan here earlier. Ryan, good to see you if you're still here. I'll talk to everybody later. So bye for now. Bye for now, everybody.